Howdy, should be recording now. Oh man, welcome back. So, Fundamental Chemistry 2, we're ready for Chapter 14. So, we are going to be looking at carboxylic acid. So, let's go ahead and jump right in here. Chapter 14, Carboxylic Acids and Acid Derivatives. Lots of learning objectives. We'll skip over a lot of that. We want to start off by a discussion of carboxylic acid groups, and so it's the COOH. So we got a carbonyl with an alcohol directly attached to it. So this alcohol is very special being attached to the carbonyl. So that's our carboxylic acid. We'll also be talking about esters, which look like an ether, but one side has a carbonyl. Right. We also want to look at some other forms of some other carboxylic acid derivatives, things that are derived from them. A little bit of a glare today. So we'll be looking at acid chlorides, chlorine directly attached to carbonyl, extremely reactive form of, it's usually referred to as an activated carboxylic acid, so very reactive there. We'll also be dealing with acid anhydrides, so like an ester, but it's a carbonyl on both sides, and it's made by taking two carboxylic acids and combining them losing water. So we'll sometimes see an acyl group, and an acyl group is just where this carbonyl, usually this other part will be just a alkane group, so just attached to the main chain, so as a side chain. So we're ready to jump into our first few pages here, so let me get us all on the same page. So the key to this is that a carboxylic acid is extremely acidic. This is caused by the carbonyl. It's already a very polar bond, and so slightly negative here, slightly negative here, and very slightly positive there. Actually, I should put it the other way. Oh man, it is positive there. How about that? It's not a formal charge. The electrons are still there, but they really spend more time on these oxygens. Now, when I have this as an acid, remember that it's going to donate H+. That's our definition for an acid. Donate H+. So donating H+ means it loses that H+, and we're left behind with this structure that has a resonance form, and so the resonance makes it very stable. The negative charge is actually distributed across both of the oxygens, right? And so that's a very stable compound, and that's what makes acids so acidic, is this resonance form. So being able to distribute that negative charge makes these things very acidic, and then having the presence of that hydrogen also makes them, not only are they really polar, but they can they can hydrogen bond with the water. Makes them extremely water soluble, and so they have higher boiling points than aldehydes, ketones, and even alcohols. Alcohols, remember, could do hydrogen bonding and were polar as well, but the carbonyl just exasperates it. It just makes things a lot more polar, and so there we go. So let's look at some uses of carboxylic acids. And I want you familiar with these uses. So formic acid, notice they're using the common names here. We'll discuss those here in a little bit. But formic acid's got one carbon, so it's a carbonyl with an alcohol, an OH directly attached to it. So carbonyl, OH, and all it has is an H over here. Alright, so that's formic acid. And that small molecule is what causes ant bites to really sting. So if you've ever been bitten by an ant and it feels like your leg's on fire, man, that's what it is. Acetic acid, we've used in the lab a lot. It's the acid found in vinegar. It's responsible for the vinegar smell that you associate with it. Propionic acid, so notice I'm just increasing the number of carbons. So propionic acid is the flavor that is found in Swiss cheese. So many people find that pleasant. It's not unpleasant for most people. Butyric acid, though, on the other hand, is the smell that we associate with butter that has gone bad, is rancid. So not so much margarine, but man, you can really tell when regular butter has gone bad. And we can also find this butyric acid in some other things, usually associated with decomposition and things breaking down and not really good to eat. And so our body picks up on butyric acid really well. Don't eat that. All right. So it's kind of interesting here that we've got these uses for it, and just changing a couple of changing the number of carbons just greatly affects whether we find it pleasant. Some of these we find pleasant. Some of them we find just absolutely terrible. Now, long chain fatty acids, what are we talking about there? We're talking 16, 18, 20 carbons in our alkyl group. And so these are going to be just long alkyl groups that have a carbonyl at the end. So we'll spend a lot longer on those in another chapter on fatty acids itself. And so this is... just use this. Alright, so we're ready to learn how to name these. And so the naming that I want to use, start off with, is IUPAC. And IUPAC, you can tell when we're doing IUPAC because it's got an OIC. So we're going to name our compound as an alkane. The carbonyl will be number 1. It's at the end, remember. And so it is possible for stuff like citric acid where we get a side group that has a carboxylic acid, but for the most part the carboxylic acid is our 1. Alright, and so you name it as an alkane, include the carbonyl, and then you drop the E and you replace it with 2 words here. You got the suffix oic and then the second word acid. And so IUPAC, you can recognize when a name is based off of IUPAC because of this O, the oic, and then acid. We'll see a lot of common names just have the ic and then the word acid. And so it's the O that really is the giveaway when it's IUPAC. Alright? So if we have more than one carbonyl, especially for our carboxylic acids, we'll keep the E and then we'll use di-tri in front of the oic acid. So it can be a little fun to say. But then one thing that we start to see a lot more than we did previously is this OH in side groups. Citric acid was our example that had that, and so that is just considered a hydroxy group, just as a little reminder on that. So let's practice a little bit. And so I've got a few examples here. So ethanoic acid came from ethane. So I apologize for the glare here. So ethanoic acid. So this is 1, 2, and so ethanoic acid. Then we're going to want to swap pens. That one's big enough. Name it like that, no problem. Hexane dioic acid. 1, 2, 3, 4, 5, 6, and you'll notice they didn't have to give the numbers. One's at 1, one's at 6. They could have also called it 1,6-hexane dioic acid. IUPAC also allows you to put the 1,6 before the di. Alright, so here's a hydroxy group. It's a side group. So 1, 2, 3. So this is at 2. This would be 2-hydroxypropanoic acid. So propane becomes propanoic acid. So this is not too bad. Let's get some. Just a second, like that, and we'll get some. Hopefully, with a little less glare here. All right. So looking at this. 1, 2, 3, 4 carbons. It's butane. Get rid of the E, add oic, and then a second word, acid. Alright, so butanoic acid. So that's the IUPAC name. Now this will have a common name as well, and the common names. Click over here. So the common names are listed on slide 9, and they're going just like the aldehydes, where we had F, A, P, B, V for 1 carbon, 2, 3, 4, and 5 carbons. So we're just going to tell how many carbons are in it. So this one had 4 carbons. It'll be B, and so that is butyric and acid. And I'll remind you that when we had 1, 2, 3, 4 the aldehyde, it was butyraldehyde, where butyraldehyde was right there, but you can see ic acid is the only real change here. So as long as you memorized your aldehydes, then the acids aren't any more difficult. We do want to be careful. The acids, when we name them with common names, we typically are going to be using the alpha, beta, omega symbols. So when we have side groups, let's make this our carbonyl. 1, 2, 3, 4, 5. Alright, so number in this, you always start at 1, 2, 3, 4, 5. So for IUPAC, it's got pentane. Lost count there. Pentane. We drop the E. Right, so then we add oic and then acid. Now it's got a methyl group at 2, and so this becomes 2-methyl pentanoic acid. Now the common name is 5 carbons. Remember, don't count that side group, but you do count the carbonyl. And so the common name then will be valeric acid, and it's got a methyl group at 2. But 2 is not usually used. You could, but typically we're going to refer to that first carbon over as alpha. Remember, the carbonyl does not get a Greek letter, and so the common name for this will be alpha methyl valeric acid. Alpha methyl valeric acid. Alright, so these aren't any more complicated. Typically, the hard part then will be trying to keep up with the name and the whether it's IUPAC or common. So let's do 3-ethyl octanoic acid. So 3-ethyl octanoic acid. I want to draw the structure from this, and so I'm going to start with drawing some carbons. 1, 2, 3, 4, 5, 6, 7, 8. You can put the acid on either end, but that automatically becomes 1. I'm going to go ahead and put that here. Remember that the O in the OH does not get a number. The numbering started at the carbonyl. It's only the carbons that are getting numbers in IUPAC. Alright, and so at 3, I needed an ethyl group, 2 carbons. Alright, so 1, 2, attached at carbon number 3. So that's not too difficult. Let's do another one. Let's do a beta methyl. Let's do butyric acid. Pay no attention to the capitalization. Again, butyric acid, 4 carbons. 1, 2, 3, 4. I'm going to go ahead and put my carbonyl over here. OH. So there's my 1, 2, 3, 4 carbons. And then I need a methyl, but don't forget this is alpha. Sorry, my lab partner decided he wants to contribute. So we're at beta, and we put a methyl group. So that's simple. Alright, so these are memorization. I might just be as simple as asking, hey, what is the name of the acid that has 3 carbons? Alright, so makes life a little bit easier. Let's do, so the common names aren't too bad. Where we sometimes run into problems is if a carboxylic acid is a side group. Now, we see this in citric acid. If it is, then carboxylic acid is attached at carbon 1, and it's actually named as a suffix. And so it gets, carboxylic acid just gets thrown in on the end. We almost never do this. IUPAC does it, but it's you don't really see it that often. Alright, so we did our common names. Aromatic rings can be a little bit problems. So remember, you can't put a carbonyl inside the ring. It would be too many bonds. And so our easiest one then, remember that this was phenol. Alright, and so the easiest carboxylic acid we can make that has a benzene ring is this one, which is benzoic acid. So it's almost like they took benzene, but it's still just a mineralization. So benzoic acid, just want to memorize it, and the easiest way of telling is it is named, so you've got a phenyl group is when a benzene ring is a side group, and a benzyl group is when we've got that extra carbon, that one extra carbon here. So that extra carbon is what we're turning into our carbonyl. Alright, so we use them in IUPAC and in common naming. And in lab, we started with, well, we're going to start with salicylic acid quite often. And salicylic acid has an OH, it's in the ortho position, remember, a 1-2 position. So salicylic acid then, that extra H there is going to greatly increase the water solubility, and so we use it for things such as making aspirin. Right? Speaking of, so let's make these carboxylic acids. The primary way we make them is from primary alcohols, and we said that we want to always keep in mind this idea of primary alcohols will oxidize to aldehydes and then continue to oxidize to the acids. And it's actually quite tough to get them to stop at the aldehydes. So the conditions that oxidize them, we usually go straight all the way to the acid. And then secondary alcohols, they will go to ketones. Tertiary alcohols do not react. All right. So that's our first way of making carboxylic acids. The other way is kind of reversing the process. If we start with an activated form of a carboxylic acid, so if I start with an acid derivative that's already very reactive, usually that's the main things we do with acid derivatives, is we make them even more reactive. And so acid chlorides, esters, and anhydrides are much more reactive than the acid itself is. And so they if you mix them with water, they react with water and they go back to the carboxylic acid form. So we can use that as our second way of making carboxylic acids. Now, the reactions that we deal with these, the first primary one that we'll be talking about is an acid-base reaction, and so we'll be losing that proton. All right. We did the citric acid lab was based off of that. And then the second one will be esterification, and that's a condensation with an alcohol. It's much like making our ether, but here we're making an ester because of that carbonyl, and it's actually a little more controllable. You don't get a lot of the side products that you would get when you have two alcohols trying to make an ether. All right. So we're set up here for our carboxylic acids. To be acids, you want to keep in mind an acid plus a base gives us a salt plus water. So this acid plus a base gives us a salt plus water. You need to memorize that. And but so when I do this, we're going to form the salts, and the salts are actually quite interesting. So let's pick this salt. If I take off an H plus, I'm left with a negative. Now this is a negative charge, it's an ion, and so it's going to pick up whatever other positive ion is floating around if I were to get rid of the water. And so in the reaction on the so our reaction in the example on the slide, it was sodium hydroxide was our base, and so it's going to grab a sodium with a plus. We can also use potassium hydroxide because it's nice and water soluble, and we'll have a potassium with a plus at the end. So whatever your cation, remember cations are positive, anions are negative, so whatever your cation is, that needs to be named first. So that name always comes first, and so in this case then sodium. And then I'm going to name the acid just like normal, but instead of the ic acid, we're going to replace that with 8. Now here's the problem. You name it by adding that oic acid, and then you replace it with an 8. And why we do this way, so ic acid goes to 8 suffix. All right, so this is so we can use this with common names. And so you can tell if a name came from IUPAC or if it came from common by looking at its name in the absence of that O. So let's name this one then. There's my sodium. Pen wants to die on me. And so number in this 1, 2, 3, 4. So that would be a separate word, so a space, right? So butane became butanoic acid. Now I'm going to drop the ic acid and put ATE. This idea of naming the acid and modifying it's just a next step from naming the alkane and modifying it. And so we will do this quite often. So this one, sodium butanoate, is the name of this salt. All right. Now, if I had named it with common naming, it would have been butyric acid. And so this would have been sodium So I'm going to have my BTRIC acid, and I'm going to put ATE, sodium butyrate. Alright, so both of these names, this is IUPAC and this is common. Both of these are expected for us to know. Alright, so we better practice number one. Alright, keep in mind this is a charge and a charge. They're not bonded covalently. Alright, so my positive charge always comes first in the name. Potassium, potassium. Alright, so potassium. I've got 1, 2, 3, 4, 5 carbons. So 5 carbons in IUPAC. His pentane would be pentanoic acid for the acid. So this will be pentanoate. Notice the O stayed. We dropped the E, added oic acid, then we dropped the ic acid. That's where that O came from. Alright. Now the common name of this is potassium, and valeric acid becomes valerate. Valerate. Alright. So practice those. They're not super difficult. We'll come back and see some things that use those again. So it's kind of hidden on this slide, is just being just a little side note kind of down here, but we will come back and use that again. Alright, so we're ready then with these deprotonated acids. What are they used for? Well, one of the main uses is soaps. So this long carboxylic acid chain, here has hydrophobic. In other words, it doesn't like water, but it does like grease and any kind of oils, anything that's not real water soluble. And then now that we've deprotonated this hydroxy in our carboxylic acid, then we have really made this polar. Alright, it's ionic here, and so this is usually called the head, and then down here would be called the tail. And so this allows the compound, the entire compound, to go into water, and then this long tail part likes to go in and just kind of grab the acid and wrap around the any kind of grease or dirt, and a bunch of these molecules wrap around it, and it drags it into the water. And so that's why we use these as our soaps. So that's one of our main uses for these long things. We'll be coming back and talking about again. So we're ready then for esterification. We're making taking an alcohol and an acid, and we're going to be combining those. Give me just a minute, and I'll take my puppy out, and then we'll continue from there. Howdy, welcome back. Sorry about that. My lab partner really wanted to participate. So, esterification is our second use of carboxylic acids and making esters really, really useful. One of the nicest labs in terms of senses, so a lot of smell. So esters, remember, had this basic feature. Carbonyl, oxygen directly attached, and then another carbon here instead of an H. Alright, so all we need to do then is use an acid catalyst. Typically we're going to use sulfuric acid or chromic acid, so some strong acid, but it only takes a few drops. Remember, all it's doing is speeding up the reaction, and it does that by activating this carboxylic acid, and then the alcohol comes in and attaches. Now we're going to be losing water, and it's the same basic idea is when we want to make an ether. We're going to draw them next to each other, and then we'll lose the water. All right, and so doing these, not super difficult. Let's start with Alright, so remember, at this point you should be able to name both of these. 1, 2, 3. This is Propionic Acid, or Propionic. I'm not even going to try and spell it, it's always fun. Just remember that you can memorize the P part for multiple choice. Alright, so this is our ethanol. I cannot spell it. Or ethyl alcohol. So I'm going to be combining these. I draw them next to each other, and then we're going to put a box around, oops, terrible, a box around water. Now ideally it's the oxygen that's in the alcohol that gets lost, but it's okay if you lose the other one. Nobody will know. And then we're going to connect the parts to the boxes. So this one becomes carbonyl, oxygen, and becomes that ether. So that's it. So let's try another one. One, two, that's acetic acid, or it is ethanoic acid. So ethanoic acid. You see why acetic acid has stuck around. So it looks like acetone, and so that's why it looks that way. Alright, so 2 carbons, acetic acid. Here I've only got 1 carbon, so this is methanol, and I'm going to draw a box around my water. I want to lose the water and just connect what's in the boxes. So what's on the outside part of that box, and we get this nice ether. Alright, so this concept here of where the acid came from and where the alcohol came from will be important later, and we can also use this if we're trying to reverse this reaction. So reversing the reaction is actually quite simple. You're going to go between the carbonyl and the oxygen, and you're just going to draw the 2 parts, adding your water back in. So I added an OH there and an H here. That simple. It's going to be key though in the naming that we remember which side and which came from the alcohol and which side came from the acid, so that carbonyl comes from the acid. Alright? So when I'm maybe that's a minute. So when I come from the acid to this ester, we change the properties greatly. So we usually associate, for instance, butyric acid, 4 carbons, nasty, rotten butter, terrible smell. But the esters have very distinctive smells, and so we use them for mixture of things. So we use them in artificial flavorings. They're found in natural flavorings, although it's a little bit tough. If you ever try artificial Laffy Taffies are a great example. So you try some of those and you say it sort of tastes like this, you know, it kind of smells that way, but not completely. Well, that's because there's much more subtlety to the flavorings in natural flavors, just because they tend to mix mixture of several different flavors. And so when we use something, say, as an artificial flavor for this, then it's just we're simplifying it. We do the main flavor, and so we're missing some of the smaller flavors. Now, because these ethers, we'll talk about their low boiling points and their very strong smells. That means they make very good communication for insects. All right, and so the smells, very small amounts of them you can detect, and they spread rapidly with any kind of breeze on a nice warm day, and so insects can pick up very small traces of them, and so they like to use them as their communication. So they're much more reactive with carboxylic acids, and even if we just have water, they'll react with water to form the carboxylic acid. All right, and so we want to get ready to name them, and the naming these is actually quite simple. You're going to do it with the alcohol will be a side group, and it gets a separate name. It comes first. Now here's what we're going to do, is we're going to treat it, this is just like when we were naming the carboxylic acid salts. So same kind of idea. The ic acid gets replaced with 8, and then alcohol part, that's going to be taking the place of our cation. So the space here becomes important. These are 2 separate words. All right. So when I'm doing some of these, let's start with this simple one we made a while ago. All right. So this one we took acetic acid and mixed it with methanol, and so now if I'm doing IUPAC, I start with the methyl becomes my side group, so this is the methyl, and then a space, and then I'm going to name the acid, and so my acid 1, 2 would be ethanoic acid. Drop the ic acid and you have 8. Notice we picked up the O in that process, so ethanoate. All right. You have to be careful on these because you're going to be tempted to use some of these common names in with the IUPAC name, and it get a little confusing on some of these. So keep those straight. Now, where students run into trouble on these is the parent group came from the acid. So let's name see how I drew it. I drew my zigzag, and then I replaced one of the carbons with an oxygen. So this helps you know that we're still maintaining our basic zigzag pattern. So this oxygen just roughly takes up the same space and the same angles as the CH2, just a little bit different angles, really close. Alright, so naming this one, you're going to be 1, 2, 3, 4, 5, 6. Remember, I'm not counting this oxygen. I'm going to be tempted to use that as the parent group. that is the side group. The parent group comes from the alcohol, from the acid. So there's two halves to each of these esters. You've got to treat them separately. And so this IUPAC name for this then will be hexyl for that side group. Alright, and then I have this acid, and again it's ethanoate. Alright, and so depending on which two acids did we used an acid, we used an alcohol, which two did we use? So we added this in. Remember, we're going to break it back down. We're splitting it right here, and 1, 2, 3, 4, 5, 6, and so this would be hexanol and ethanoic acid. So I might ask you which two acids were used to make this, or maybe I'll give you the name. You have to figure out the structure and then figure out these. So a little more critical thinking on these ester questions. Besides just the naming, we also want to know, if you can tell, how they were made. And so you just got to look for that carbonyl. That's going to be our key determining factor here. Alright, so I said that these were used in artificial flavoring. So let me give us our full board on this. So ethylbutanoate, pineapple. So remember, butyric acid, rotten butter, just putting an ethyl group on it, and gives us the smell and the flavor of pineapple. Mostly the smell. All right. So isobutylmethanoate is considered. So that's a mouthful. Isobutylmethanoate. So let's figure that one out real quick. So isobutylmethanoate. So 1, 2, 3, 4, and then I'm gonna have my oxygen. All right. It's iso. Wait. Iso. I need to take one of these off and put it here. 1, 2, 3, 4 with an iso group. All right. Let's see. And then methanoate. So this came to 1 carbon. So that's going to be an H there. It was methanoic acid. All right. And so pretty straightforward looking compound, not too big, gives us the smell of raspberries. So that one's not too bad. That one's hard to pick out in the lab. Raspberries are a tough flavor. Now this bananas ethanoate, we saw that. It's ethanoic acid, and then a 3-methylbutyl, and then 1, 2, 3. It's basically an isopentyl group, but 1, 2, 3, 4. There we go. A 3-methylbutyl ethanoate. This compound is used to make bananas. Now, this is going to make artificial smell of bananas. If we make it in the lab, it smells just like banana Laffy Taffy. Now, one of the problems with that is we associate that smell. A lot of people really like it, and so you might be tempted to say, oh, well, it's you got a very low boiling point. Let's put it on our just rub a little bit on, and it'll make perfume, and you'll smell like bananas, and that'll be great. So first problem is, keep in mind, these are very reactive. So esters react with water and a little bit of acid, but really just a little bit of water, and it falls back apart. This one we would get back in alcohol and acetic acid. So you'd start off smelling like bananas and end up smelling like vinegar. All right. Not too bad here. The pineapple, start off smelling like pineapples, end up smelling like junk butter, so junk rotten butter. Just not very good. But there's a much bigger problem. Not only are these going to break down and start to stink, This one in particular, for the banana flavoring, this is used as the attack pheromone for bees. And so if you were to wear this and then walk past a beehive, so when the bee, once one bee stings you, it releases this compound and it kind of labels you. And so the other bees know, hey, we need to attack, and this is the target. This is what we're attacking. This is the threat. And so you can see how this would be bad. All right, and so that compound, nice and easy, not too bad though. So Octel Ethanoic. So again, starting with acetic acid vinegar, and we're going to be adding an octyl group, and it gives us this orange flavoring. All right, so that's not too bad. Methylbutanoic, hey, butyric acid again. Remember the rotten smell? Just adding a methyl group. We added an ethyl group. We got pineapple. We had a methyl group. We got apple. So adding a pentyl group there. You got apricots, and then thiobutanate. We're doing a thioester, so started with a thiol instead of an alcohol, and we get strawberries. That one again is a little bit tough to smell in the lab. So the problem with these is these artificial smells and flavors. They're used in so many products that they're hard to tell. Some of these you may think, oh, this smells like oranges, and then other people say, no, that smells like Lysol, or it smells like car wax. And so you can make these a little bit tough to identify. All right, so I mentioned that these will react with water, and so when they react with water, they just break apart, they split. And it's just an exact reverse of the previous one. So if we do this reaction, this is referred to as acid catalyzed. So this is a hydrolysis. We're breaking it apart. Now, this reaction can also take place in basic conditions. Now, basic conditions, so we're looking here at just a second. Basic conditions, we're really looking at breaking this apart using the base catalyst. Alright, base-catalyzed saponification. This comes from a story of how we found soap. Supposedly it was mountain sapon, alright, and they did a lot of animal sacrifice up on the top of the hill, and every time it would rain, it would soak up all the fats from the animal where they had burned it, and so that animal, all the grease and the fats, would get washed down the hill. Alright, and as it did so, it would react with the wood. When they burned the wood, they ended up producing potassium hydroxide, and so that reacted with these fats as it washed down the hill, and so people would come from all around to wash their clothes in the creek that ran at the base of the hill, because it would be soapy. Alright, and so that's where the soap comes, that word soap comes from. And so it would, they'd wash their clothes there, and it was because of this reaction between the base that was found in the ashes and in the fats. Alright, so that's a saponification. And so when I want you to use a base catalyst, I'll always do saponification. So I really want you to know in this name. So acid catalyzed we'll say usually just say hydrolysis or acid catalyzed hydrolysis. Now saponification is a hydrolysis, but it's a special name, a special case. And so if it says saponification, it's always base catalyzed. Now you don't actually make the acid because the acid would turn around and react with the base. And so you end up with the salt and your alcohol back. Alright, so keep in mind it's always the acid that's going to be deprotonated and not the alcohol. And typically then what you would do is take the soap and add a little bit of water, or you'd collect this, you'd remove the water and get this salt that had the long fatty chain with our deprotonated carboxylic acid, and you got a nice greasy soap, and you would make that into a bar of soap. All right? So give you a nice picture of this. We could search on YouTube and find all kinds of videos of hand making soap, but it's not super difficult. And so here we've got our fats. Now this one we'll see later. This is a triglyceride, right? And it is based off of this alcohol, alright? And this is glycerol. It's got that kind of E looking shape. Now if I drew it like this, it's harder to see that shape, but this is glycerol. So if we take this as our alcohol, we can actually attach 3 carboxylic acids, and then all we're doing here is reproducing this. So the animal fat is mostly glycerides, and so it's got these going to have these esters here, and we're going to break the ester linkages. KOH, so potash lye. So when you have to make your own soap, what you do is you say every time you cook and every time you kill an animal, you save the fats. You kind of save them for maybe weeks or months, depending on how much you're using. And then you would also save the ashes every time you made a fire, and then you would soak those ashes in water and get out the potassium hydroxide. Now it's very caustic, so you would use it in this. You'd see them having big pots. It looks like a witch's cauldron, and they're stirring these things with long handles. Usually looks like an oar. All right, and so you're going to stir that and heat it over a big fire and get it boiling, and then you add in these and so adding in some heat and some water, and these fats end up making the soaps. All right, and then you boil away all the water, and the glycerol is a liquid, and so it's pretty easy to separate out from your soaps. And even if you don't, it's a natural lubricant, and so leaving a little bit in is not a problem. The main thing is you got to wash out all the KOH, so any of that left behind, you really got to get out of there. All right, so so then we're ready for our carboxylic acid derivatives. We already talked about acid chlorides, acid anhydrides, where we've taken 2 acids together and made those together. So let's look at making one of those real fast. It's the same idea as making ethers and esters, and so let's pick on acetic acid. Alright, so if I take 2 of these and I react it with some, you can do it in acid conditions. So the acid conditions, main thing is we want to lose water. You draw 2 of these. And then you just draw your box around your water, and we're going to connect them. So this would be, and the common name would be acetic acid anhydride. Acetic acid anhydride. So these are also related then to phosphoesters. Now, phosphoester uses phosphoric acid. So phosphoric acid, notice we've got 3 OHs here, and so we can actually attach in several places. So we just take an alcohol, and we use this in our bodies to part of our energy production. We'll see these compounds quite a bit later chapters. We mentioned a thioester when we were talking about our common uses for esters, and so it's just using a thiol and SH instead of an alcohol, and so you get this thioester. If we want to use this, a lot of times they use it to get that carbonyl, and they want to transfer that on someplace else, and so our body likes to take that and use that as a transfer. And polyesters, remember poly means many, so polyester is just a series of ester bonds, and they come together, and usually we make these with 2 different monomers. So one's got an alcohol on both ends, and one's got an carboxylic acid on both ends, and so you mix A and B in equal amounts, and then you get a big long polymer chain. Now the problem with that is if you don't get the exact right mixtures of those, then you get shorter chains, and it can be a little bit finicker. And so you can solve that by using a compound that's got an alcohol on one end and carboxylic acid on the other. The problem becomes trying to keep it from reacting with itself, and so you have to keep those very cold, and you might not be able to keep them around very long, and so they react really well, almost too well. And so this A and B approach of mixing these is nice because you can put this right into a mold, or you can draw it out. So if we were to make this into in a container, that we would be able to draw it out and pull it up into fibers. Okay. So that concludes our chapter on esters and carboxylic acids. The main thing is the naming and this idea of saponification and acid hydrolysis, and then being able to predict esters, which sides came from the acid, which side came from the alcohol. So we'll look at some problems on this in the next video, and then we'll be getting ready for that 3rd exam, and getting on almost, we're really close to the biochemistry here. We've got a lot of the chemicals and compounds that we need. We're already getting into where their uses are in biology. Alright, so we'll stop you there and see you on the next one.